this thing where I have my speaker notes on my phone and I can hit a button and the slides advance, that's not going to work at all. So I'm going to be awkwardly going back to them. Oh my God, it worked. All right. Yes! Web apps, everyone. So hello, my name is Laurie. I am the CTO of NPM, and in case anybody is confused, I am not the famous NPM guy. The famous NPM guy is Isaac, and I am just the guy that he picked to run his engineering. And what are we talking about today? This is a talk not about how to write Node code, because there's a fair number of those at this conference. This is a talk about what I do is I run a really popular web service that consists of dozens and dozens of Node apps. And this is a talk about how to do that. It's about how to run the whole system, not just how to write one particular piece of software in Node. And specifically, it's about service-oriented architecture, or SOA, which is the architectural pattern that we use at NPM, and we are big fans of SOA. So specifically, what I'm going to be talking about is what SOA is, in case you're unaware of it, why I think you should use it, why you should do it in Node specifically, why is Node good at this stuff, how to do it properly, and a case study of how we use SOA at NPM, because we've been doing it for 2 years now, and we've picked up some tips about what we think works and what we think doesn't. My hope is that by the end of this, you'll understand why we like it and have a pretty good idea of how to apply it yourself. But first, a quick confession, which is that yesterday I had a whole different talk. And at around 4 o'clock, I had a really interesting conversation with my VP Eng, and I was like, I should do that instead. So I threw out the middle half of this talk and replaced it with a completely new talk. So it's somewhat unrehearsed. I think you'll like it better than the old talk, but be warned. So what is SOA? It's a design pattern. Somewhat formally, it is a design pattern in which the logical components of an application are separated into standalone services that communicate via defined protocols. Much less formally, it means splitting your app up so it runs on lots of boxes. As in this drastically oversimplified diagram here, on the left you've got the more traditional monolithic thing. You've got one big machine and everything's happening on that big machine. And this is the sort of platonic ideal of the SOA, where every single thing that is happening on its own box. Usually the protocol that these things are speaking to each other is HTTP, but it can be anything. It can be Thrift or Avro or buffers or whatever the hell. To dip into slightly academic terminology just for a second, an SOA is an example of a distributed system. And distributed systems have some really interesting properties. The first is concurrency. Concurrency meaning that there are many actions happening interleaved with each other, not necessarily in parallel with each other, although that can happen as well. And there is no global clock, which means that actions can be happening at different speeds in different parts of the system, and you cannot guarantee that things that happen in one order will always happen in that order. The third crucial attribute of them is that they have independent components. And independence means not just that they're on separate machines, but that a failure in one part of the system does not create failures in other parts of the system. It is very easy to move your giant monolithic application into lots and lots of boxes and have it still be a monolith. It will still, if the front door fails, everything else will fail, then it's not really a distributed system. It's just a really big monolith. And these are super interesting properties for a web service, and as we'll see, they lead directly to the advantages of an SOA. You may also have heard of a pattern called microservices. There is a difference between SOA and microservices, and that is that one takes much longer to say. Other than that, there's no real difference. They're the same thing. They are small, focused services talking to each other over the network. And if you think that there is some big difference between them that I missed, feel free to put your hand up in the QA section and be that person. But for this talk, I'm going to be using them interchangeably, and you can consider them interchangeable terms. So, am I going too fast or too slow? This is the thing about being unrehearsed. So, let's talk about why SOA is a good idea. There are two types of reasons that I like SOA. The first are technical, architectural reasons, and the second are organizational, human reasons. Let's do the technical ones first. The first technical advantage is resource efficiency. Imagine you have this big monolithic app that does all sorts of stuff, but it's mostly getting one type of request. It's getting this one read request over and over. To run, it needs to have everything that it can do in memory, but it's really only doing one of those things. So even though you're only using those 4 bits of your software, you have to use all of your memory. You can only fit 4 of these processes into memory at the same time. If you instead run a microservice that does only that thing, you can, in this imaginary box that I have drawn on the screen, fit twice as many processes into exactly the same amount of hardware with no change to what you're doing other than a change in your architecture. This is obviously a stupidly oversimplified version of this principle, but take me at my word when I say that this works whether or not your constrained resource is memory or disk or processor or network or whatever it is. The next technical advantage is cost efficiency. By splitting your functions into separate machines, you can buy hardware that is specialized to those purposes. So if you need high memory or high CPU or high disk space, whatever, and it also means that you can scale the hot part of your application without wasting money. If you have 7 services that make up your machine, and one of them is your front door, and your front door gets 10,000 requests per second, but one of them is your login service, and your login service gets 1 or 2 requests per minute, if you're in a monolith, you have to buy 10,000 requests per second worth of boxes, and you've scaled everything. Suddenly your login server can do 10,000 requests per second, but it doesn't need to. In an SOA, you can just take the hot part of your application and scale that, which means that there's less risk because you're scaling only that part, and you don't have to think about what happens when you scale your login server, and it also means that you're just spending less money doing it. You can also tune your redundancy. So again, with that front page example, you never want your front page to be down. You always want your front page to be up. So you're going to buy tons and tons of those boxes, and you're going to make sure that they're multiply redundant such that a failure of one of them doesn't take yourself down. But your marketing pages, you're probably not so worried. You're probably OK with your marketing pages having 98% uptime and maybe half an hour to restore them if they go away. So you run you run dozens of servers for your homepage, but only one server for your marketing origin server. And again, you're saving money and you're saving time because you don't have to solve the complicated problems of high availability for a marketing server. The next technical advantage is robustness. Remember I said in the formal definition that service-oriented architecture means a failure in one part of your system is isolated from the other parts. That's really great for robustness. It means that if the intern makes a bad deploy to one service, it doesn't take down your whole application. If in a monolith, if the intern made a bad deploy and was suddenly throwing a fatal exception all the way up through the stack, your whole app would be down. Your whole company would just halt. But in a service-oriented architecture, only the thing that they were messing with that day is down, and it's probably not the most crucial thing in your application because you gave it to the intern. So at most, it's going to take down one service, and that's cool. And robustness also applies at the hardware level, which is just simple math. Assume that you are using the world's worst hardware, and it has a 1% chance of failure on any given day, which is significantly worse than any actual hardware. And imagine you have 100 of these boxes. The chances of all of those boxes failing at the same time is this gigantic number, which I enjoy printing out. It's basically 0. But the chance of one box failing on any given day is exactly 100%. You will definitely lose one box per day with this 1% hardware because you have 100 of them. So this means 2 things. First, it means that you need redundancy in a service-oriented architecture. You can't have only one kind of any service up because the chances of you losing that thing are pretty high. Or if you don't care about it being down, you can. But the second is that you need to be really good at replacing hardware because when replacing hardware when you have 5 boxes is a thing you do every couple of months, and it's OK if you have to relearn how to do it, and you're like, oh, where are our app servers? We don't even remember. But in a service-oriented architecture, this becomes not a daily thing, not even with the world's crappiest hardware. It becomes like a weekly thing, probably. So you have to automate the hell out of your deploys, otherwise you're going to spend all of your time doing that. But the payoff is that you'll basically, all of these things are a lot of work, but the payoff is that you'll basically never be down. You'll be this thing, which is really cool. Since prior to 2014, NPM would go down for hours at a time. If it went down at 10 at night, we wouldn't notice until the next morning, and so it would be down for 8 hours, which was great for our reputation. But as of 2014, when we actually formed a company and started doing this, NPM's registry uptime has been 99.998%, which is 10 minutes per year. It's probably going to go down right now as a result of me making this boast in a talk. Another simple but invaluable advantage is debuggability. It's really simple. It seems like an obvious thing, but because only one box only ever has one service, you know that if that box is in trouble, that service is in trouble, and vice versa. You know if there's something weird happening on that box, it can only be that service that's causing it. You've eliminated a whole step in your debugging. So Their services are easier to debug for that reason, but once you get into the service, because the services are themselves simpler, the services themselves are also easier to debug because there's just less to them. They're smaller. There's only a certain amount of unique code in each service because they're each doing something very simple, so debugging it is usually pretty simple. You're like, oh, there's 200 lines of code, and this one has a semicolon in the wrong place. But strangely, even despite those technical advantages, which I like, the real advantage of a service-oriented architecture for us, and I think probably for you, isn't about the technology, it is about the organization that builds the technology. If you've ever heard of Conway's Law says that software reflects the structure of the organization that built it. So if you have a small, fast, lean team, you will tend to produce small, fast, lean software, and if your team is an 8-way Byzantine feudal war, then you'll have Windows or something. But the reverse can also be true. You can structure your software such that it demands that teams be in an efficient structure. You can demand that your software is built in a way that makes for efficient teams. So the first organizational advantage is simply that simpler systems are simpler. Each individual service is a small, isolated domain of understanding. It has limited and easily understood inputs and outputs. And that makes the whole service easier to fit into one human brain. And that's really important because the human brain, the size of a human brain, the capacity of a human brain is one of the hard and immovable limits of software development. You cannot make a system that is larger than one human brain without things going rapidly off the rails, which is not a Rails dig, but it should have been. So because your services are smaller, you can give those services to smaller teams, and that is important because communication within a group is another one of those unfixable people problems in software development that we cannot get rid of. So imagine you've got this team of 5 people, A, B, C, D, E, and communication within this group is not n. It is not the number of people in the group. It is not even n squared or n factorial. It is basically infinity. You can easily imagine A has to talk to B and C, and then they talk to D and E, and they discover that E had some information that A didn't have before, so E goes back to A, and A talks to C again, and then B is like, oh, I was sick that day, and I missed it, and suddenly everyone is angry and confused. And this will go on for a little while, and eventually the information will ping-pong back and forth, and maybe a day later, everyone will reach equilibrium, and suddenly everything will be happy again. But if your team is bigger than this, if your team is even twice this size, that basically never stops. If you've been part of a 50-person engineering team, and I really hope you haven't, you will understand what I mean when I say that the anger and confusion is basically continuous. There's no way to get a team of that many people all on the same page, all at the same time. It just can't be done. There's only 24 hours in a day to be talking to people. So the smaller your team, the more likely you are to eventually reach equilibrium and actually be able to get things done without getting people very angry and upset. So because smaller teams have better communication, they can move faster, but there's not only that. Because that team is working together on a smaller system, because they can fit it all into their brain at the same time, they will have a better sense of ownership. If the team feels they own the code and they can fit the whole system into their brain, they're going to be more fearless about refactoring. They're going to be faster at debugging. They're going to write more comprehensive tests, and they're just going to be writing better software. We are better at writing smaller software, so the solution there is not to find some magical way of writing big software, it's to make sure our software never gets big. So that is the fly-through part of why SOA is great, and this is where we are entering unknown territory, because this is where I threw out the rest of the talk that I'd written yesterday. Because in the previous version, I was just talking about all of the pitfalls of SOA and the things you need to avoid, and I was like, that seems like a real downer to go out on the talk with, so how about instead I say what I think you should do to actually make this SOA work for you? What are the things that we found that worked and the things that we found to avoid? But before I go into that, I said at the beginning that Node is particularly good at SOA, and why is that? So firstly, and most obviously, Node is just good at web services. When Ryan Dahl invented Node, tiny web services were exactly what he had in mind. They're native to Node. It's what Node expects you to do if you're not doing anything else. The hello world in Node is like build a web server that prints hello world. And Node is really great if your workload looks like a web app. If your workload is highly concurrent and I/O bound, then you're going to be really good. You're going to be writing Node that is really working with the grain. Node is really good at being high concurrent and I/O bound because that is what we were trying to solve at the time, and that is a perfect fit for an SOA. And the next reason is Node's cultural pattern of creating small and simple modules that we use together. In other languages, because libraries are hard to use, you tend to get these big kitchen sink libraries, only 2 or 3 of them per project, and they do a bunch of stuff, which means that, per my example earlier, you have a lot of stuff in memory all the time that's not doing anything. It's just sitting there using resources for no reason. So simpler modules that do only the thing you want mean really fantastic efficiency. But finally, the big reason is that shared logic is easy in Node. And the reason that shared logic is easy in Node is because, not to toot my own horn or anything, because of NPM and because of the Node module loader. So part of the reason that Node has small modules is because small modules are easy in Node. And the reason small modules are easy in Node is because of NPM and the module loader and the way that they were built at the same time with the expectation that they would both be there. NPM puts stuff into the Node modules folder in a pattern that the module loader is expecting, and the module loader loads stuff out of that structure on disk in exactly the way that NPM was expecting it to, and they work hand in hand, and that is a unique feature of the Node runtime system. No other runtime system was built with the expectation that a package manager would be there. Package managers were an afterthought or a secondary feature of every other runtime. So people often credit NPM with this idea that NPM eliminates dependency hell, but it doesn't. The Node module loader eliminates dependency hell, and NPM just sort of helps. But because you can load multiple versions of the same library into memory at the same time with the Node module loader, it means that dependency hell doesn't happen, and that means that you can be fearless about including as many libraries with all of their subdependencies as you want, because you know they're not going to fight with each other, because it's literally impossible for them to fight with each other in Node. It just can't happen. So because of all of that, Node and NPM let people share libraries frictionlessly. But you still have little bits of internal logic. Not everything that you publish, not every module is a global module that you want to share with the world. So if you have stuff within your company that you want to keep within your company, but you still want it to be a module because you want to share it within different parts of your SOA, then NPM has always let you do this using private Git repositories. You can just set your dependency to be a Git repo, and it will pull it down. But in the last year, we have introduced NPM organizations. Those let you create teams of people within the NPM registry and share modules privately to only that team. That is really great for smaller companies, but if you're a bigger enterprise company and you want to use your internal sign-in, or you have really strict security requirements, or you have strict licensing requirements about which types of software you can use, then we built NPM Onsite, which I'm going to talk about very briefly later, which will do that stuff for you. So it's all very well me telling you that you should build an SOA because it's great, and that you should build it in Node because Node is great at SOAs, but how exactly? So like I said, we spent 2 years building a SOA in Node, and we've picked up a few things that I thought would be useful to share. And they apply at the application level, at the architectural level, and at the operational level. The first application level principle is isolation. You should isolate your data sources. Each data source should be talking to exactly one service. You should not trust your services to respect each other's data integrity, because that usually doesn't work out, especially when you have a big team that are fighting with each other. So if you do that, if you set one service per data source, how do you square that with the idea that your service should have only one task? Your service should be as simple as possible. What if I have 2 types of tasks that require the same data source? And the way to get around that is to be rigorous about splitting the data. The example that I use is if you have 2 services that both need to talk to the data source, but their functions are not really aligned, but one of them is editing and writing to the data source, and one of them is only reading to the data source, you don't really need them to be talking to the same data source. You can create a mirror or a copy of the first data source and have one service talking to that and one service talking to the other, and you can just have replication or some other form of copying to make that happen, which has other advantages, which I'm going to talk about in a bit. And another hard lesson we've learned in an environment that has 17 services, that is what makes up the registry, is that those services need to be consistently designed, or you will spend your whole life confused. You'll be constantly going, oh, how did we invent logging in this one? How does this one find its configuration? And how does this one remember who the user is? So you should be logging consistently, not just the requests, but the results of those requests. Logging failures is great, but logging success is important, because if your Node application crashes and all you've seen is a request and nothing after it, that looks like success, because nothing happened. You didn't see a failure get logged. But what actually happened was a terrible type of failure, where it was such a big failure that it didn't even manage to log a failure. Because success is not merely the absence of failure. And speaking of that, we have developed really strong opinions about how error handling should work. If your service doesn't know what to do, if it gets into a corner that you weren't expecting, if the programmer was like, this can never happen, your program should crash. That is what it should do. And it shouldn't just crash and your whole service should go down. A parent process should be watching it for crashes and restarting it as soon as it crashes, because that is the best kind of recovery. Any kind of recovery where you're like, all right, well, it crashed, so we're going to have an exception handler at the top, and we're going to try and recover state and put things back to how they were and start again, it is doomed to failure, because if you could expect how it was going to fail, it wouldn't have failed that way. So by definition, the only reason you're going to be hitting a crash bug is if something really weird is going on, and you won't expect that weird way, so you won't be recovering accurately from that state. So instead, just crash, because then your program will start again, and it will start again from a known state. It will start again from the beginning and go, okay, this is point 0, I know how to go from here. Obviously, if you've designed a system that just crashes all the time and restarts all the time, that leads to a situation where you can just be like, oh, we didn't realize it crashed 300 times a second and that was fine. So you need to put some monitoring and some metrics around that. You should need to know how often your service is restarting itself so that you can check if you've got a crash bug. But most importantly, your services must share logic. I said that was easy. So your logging should be a module. Your monitoring should be a module. How you load configuration should be a module. They don't have to be a global module that somebody else wrote. If you need to do something weird and specific to yourself, or you just need, you just have your own requirements for doing that, make it your own private module. But it should be a module, and the code that is part of your service should be only the code that is unique to that service. The smaller you can keep the volume of unique code in your service, the easier it's going to be to debug. I was talking at the beginning about how it's only 200 lines. A lot of our services are only 200 lines, and that's great. It doesn't mean that we've been profligate with a number of services. It means that we can debug things with one screen of code, which is super useful. So the less unique code, the easier to debug and the easier to understand. And next we come to the architectural principles. First and foremost, get used to being asynchronous. Many fewer things need to be instantaneous than you believe. You do not need to be transactional about everything. Be as eventually consistent as you can possibly get away with. Use queues liberally, both for input and for output. We use CouchDB, which turns our entire database into basically an event queue, which is basically the only thing that CouchDB is good at. And that's an incredibly useful pattern that I'm going to talk about in a second. And you should also be handling back pressure. When a downstream service says that it is too busy to absorb your requests right now, your upstream service should be able to queue those up, back off, and say, OK, I'll start sending these again when you're ready. Because your architecture is distributed and networks are inherently flaky things, you need to expect that and you need to handle that. You need to detect a network timeout. You need to detect a network hang. You can't just assume that everything is going to work the way that it's supposed to. You have to expect that sometimes Amazon's going to have a hiccup, and this thing that you thought was an open TCP connection is just going to hang for 60 seconds and going to be like, all right, I need to drop this because nothing has happened. So, and when you've done those things, you need to recover automatically. You need to retry automatically. And once you're doing that, you need to avoid thundering herds, which is when you have dozens of boxes that rely on a service, all of which have seen that that service has gone away, and when that service comes back up, they go, oh, thank God, and they all jump on it at the same time, and it goes down again. They have to be backing off. They have to be expecting that there's going to be other services around competing for the same resource. So you should also be failing softly. Can you serve stale cached content if your service is down? A lot of the time you can, and if you can, you should. You should fail safely if your authentication service is down, but there's some class of things that it does that don't require any authentication. Its failure mode should be, well, this doesn't require authentication anyway, so I'm just not going to ask the authentication service. It's down. I'm just going to go merrily on serving this public content. And the last architectural thing is that a distributed system has race conditions. It will have lots and lots of race conditions. Anything that can happen out of order will happen out of order. And stuff that usually takes 1 second will take 40 seconds unexpectedly sometimes. People will try to publish the same version of the same package at the same time from 30 different boxes. That was a thing we were like, when we designed the system, we were like, no one's ever going to do that. It's no problem that there's a race condition about that happens. No. People were doing exactly the same publish from 30 machines at the same time because that was their build farm. And every single box in their build farm would try to publish the package at the same time. We were like, you can't do that. You can only do one package publish of one version, and the other 29 are going to fail. And they were like, we don't care which one. I'm like, OK, I guess we have to handle that now. But the problem with race conditions is that there's no magic bullet. There's no piece of advice I can give you that's like, and this will mean that you never run into race conditions. The only thing you can do with race conditions is be aware that it's nearly always going to be a race condition. Finally, there are the operational lessons we learned. Your configuration should have a central source of truth. We tried it every other way before we tried that way, and all of the other ones sucked. We use etcd to save our configuration data. etcd is itself a distributed system, so we cram all of our distributed information to this other distributed system and hope that those programmers were better at distributed systems than we were. And your services should pick up that configuration at deploy time, not at startup time, and definitely not at restart time. Your service should only change its configuration when you were explicitly expecting it to. Because any kind of system where you can push configuration to all of your machines, you're going to accidentally create a bad configuration, and you're going to destroy all of your machines at the same time. A distributed system doesn't work if the components don't fail independently. And if you have a system where all of your services are constantly getting pushed configuration, or they're occasionally polling for configuration, then you've created a single point of failure that is your configuration. And getting it wrong will take out all of your services at the same time. So, as I mentioned earlier, deployment in SOA is constant. It's no longer this thing you do once in a while. It's this thing that you do every day. Whether you want to or not, boxes are going to fail frequently, so you need to automate the hell out of your deploys. We use Ansible to automate our software deployments, and we are moving to Terraform to do the hardware deployment as well, which is a really cool system. So now you can just say, OK, this system exists on a box of this size, and it has all of this software on it, and I'm going to hit a button, and it's going to create the whole box and put all of the software on it and plumb it into place with all of the networking, which is super cool and eliminates a whole class of job at NPM. We also find canarying extremely useful. That is where you deploy new code to production, but only for 2 to 3% of traffic. Because you have code and you've tested your code, but you tend to test code with the data that you were expecting. You test code with the data that you thought would be there. And the problem with production traffic is that people do really, really weird things in production. People are like, yeah, I know that you're NPM, but I was expecting a Maven repository, so I'm going to send you thousands of requests for Java files and see what happens. We used to throw a lot of 500s for misconfigured copies of Artifactory, which for some reason thought that we were a Maven repository. So putting the canary in for 2 to 3% of traffic, it means that deploys take longer because we have to sit the canary there for 24 hours to make sure that nothing really weird happens. But it means that if we've done a crappy deploy, the worst that can happen is we temporarily inconvenience 2% of our users, and the other 98% of our users don't notice that we did that terrible deploy. And there's one other trap, which we found it crucial to avoid, is cold starts. This was when GitHub went down last week for 2 hours, this was the problem that they were having. If all of your services are down, can you bring all of your services back up? That sounds like you should be able to do it, right? But once you're running a really distributed system where there's tons and tons of boxes, you get used to them being there, and you begin to optimize for the case of deploying one new service inside this sea of other services. So what GitHub did is they ended up with a service that was relying on its Redis servers to already be up so that it could start its application server. But instead, there was a power failure that took everything down at the same time. And so the Redis server couldn't come up, and the application couldn't come up because Redis wasn't there. And Redis was relying on the application server to be there to be able to come back up. And that is why they were down for 2 hours, because they had to fix that. So to solve this problem for us, there is a tiny little copy of the registry which exists only to allow the registry to deploy itself. Because if the registry is down, you can't install the node modules that make up the registry. So there's a tiny little registry that only deploys the registry. And it sat there for 2 years and has been used exactly once in that 2 years, but that one time was extremely important. The next thing is metrics. Metrics are crucial to running an SOA. Because there's so much more of your system to understand, and it can fail in so many more ways. So over time, new hotspots are going to emerge. Services that used to be fast are going to slowly slow down as new code is added, or the performance characteristics will change in other ways. So you need to capture everything that is going on in your system, like request sources and frequency and size, and your response types and their size and how fast they happen. And just every type of event that you can think of that happens in your system, you should just be throwing it at some kind of metrics server. And once you've got all of these metrics, you should be doing stuff with them, and you should be doing stuff with them in advance. You should be creating real-time dashboards, and real-time dashboards feels like this sort of enterprisey thing that nobody really needs, but the fastest form of debugging is to be able to pull up a dashboard of graphs and go, whoa, that one has a huge spike in it that wasn't there yesterday. What is that spike? That is how we debug stuff about half of the time. We're like, oh, one of the pretty pictures is really weird looking today. That must be the bug. So you can do it that way. You can do it just by visual inspection. But if you really want to get fancy, you can start putting monitoring around the normal values of your metrics. You can say, this is the range in which this metric usually exists, and I'm just going to trigger alert as soon as it drifts out of that. You don't have to wait for the system to actually fail. So that is all of the stuff that we learned about running an SOA and how to run an SOA well. And I figured that showing you how that actually works in NPM is a good idea, but I left it until last in case the rest of this was over time, which it seems it's not quite yet. I have like 7 more minutes, right? So what is NPM? You'd think I'd have had to cover that first, but you were all sort of, just winging it. NPM's this thing in the cloud. NPM is 4 things. NPM is NPM the CLI, the command line client that you run every day. NPM is the registry, the public registry at registry.npmjs.org, which is where the client downloads and publishes the packages. And it's NPM the website, which we call DubDub, which is the primary NPM website where everybody reads packages and documentation. And then there's NPM onsite, which is a tiny copy of NPM, which runs inside the firewall of big and hopefully price-insensitive corporations. Fun fact, we did a poll yesterday and found that something like 21% of NPM's users think that NPM just downloads stuff from GitHub all the time. So if you're one of those people, now you know. We run a bunch of servers, and they have the tarballs on them, and that is what NPM is doing. It's downloading them from us. I kind of want to run like a follow-up poll, which is like, what do you think all of these people I hired do? Like, do you think they all run the website? Because the website's not nearly as good as 27 people would expect. But back to the architecture. What may not be immediately obvious from those 4 things is that they're actually really one big thing. They're a single gigantic service-oriented architecture with shared services and shared logic, and I can show you how that works. This is the simple version. You can see users talking to the CLI on the website. Both the CLI and the website use our CDN. The CLI and the website both use the registry. On-site users hit their own copy of on-site, and on-site itself talks to the registry. Here is the less simple version. I should be honest that this diagram is meant to be deliberately confusing. Its file name is shitshow. It is accurate, but it's not even complete. There's actually more stuff than this in this diagram because we tacked on a couple more worldwide servers recently, and there's a couple services I didn't picture. But I can break it down for you. First is the CLI. It's sort of arguable whether you can consider a command line client to be part of a service-oriented architecture because it's not a server, right? But the reason I do is because there is shared logic. There's not as much shared logic as we would hope. In fact, basically the only thing that is shared between the CLI and anything else is the bit that validates what is the valid name of a package. But it is shared everywhere. It's the command line client thinks it, the website thinks it, the registry thinks it. And also the CLI is the largest consumer of the registry. So when you're thinking of creating contracts between the services in your service-oriented architecture, you have to think, what is the CLI going to do? The most complicated portion of our architecture is the registry. In simplified form, it looks like this with the bottom cut off. There's a CDN that does a ton of caching, which is why everything is nice and fast. And all of the cache misses go to our front door service, which is essentially a router. The front door calls the auth web service to authenticate every request, and a lot of interactions with the registry are anonymous. So that's often very simple. I was saying earlier that if you can get away with it, just don't talk to your authentication service, and that is what we do for 99% of requests. 99% of requests are for packages that are obviously public and will always be public, so we just don't bother to talk to our authentication service, which means that our reliability is good and our hardware requirements for that service are really low. Behind the auth service is the access control list, which if you're not a public package, it's like which of the users is allowed to see this. And further behind that is the license API, which is if you're a paid customer, have you actually paid for all of this stuff that we're doing for you? Continuing our Lightning Registry tour, is the delightfully named Validate and Store service, which, as you imagine, validates and stores packages. It stores them in 2 places, in the binary store and the metadata store, depending whether it's the package JSON or the actual binary file. And the binary stores are literally just computers with very large hard drives. We went with lots of other complicated ways that you can do that, and we were eventually like, file systems are really great and they're really efficient. Let's just cram everything onto a file system and put a lot of replication and backups in there and see if everything works, and it does. If you're installing a package, then it's just going to go straight to the binary store and pull it straight out of there and send it through to the CDN without talking to anything else. Tacked onto the right, you will see that there's a set of services which are a relatively recent addition called the followers. I said that we use CouchDB as an event queue, and the followers are what are using CouchDB as an event queue. They basically listen for every single publish event, every change that happens to every package on the registry, and they look for things, whatever those things are that are important to that service. So there's one called the credentials follower, which is unpacking packages and seeing if you accidentally left your password inside the package or an auth token of some kind. This used to be a big problem with the registry. There were lots of people who had dot files inside of their packages that had all of their credentials, and now that doesn't happen anymore. If the credentials follower finds that you've accidentally leaked your tokens, it unpublishes the package and it sends you an email going, hey, you did that thing. That was pretty dumb. There's also a tarball follower. Like I said, we're a really distributed system, and we had this problem, which is that if you publish a package, that package needs to go to all of the servers worldwide, which meant that publishes, the more worldwide points of presence we added, the slower the publishes got, because it had to copy them not just to you, it had to copy them to the West Coast and the East Coast and Australia and Asia Pac. So the tarball follower is how we fix that. The tarball follower lets you publish to just one of the locales, whichever one you're closest to, and then the tarball follower listens for that event and copies it to all the other ones. That creates, obviously, a race condition where it's possible for somebody in Asia Pac to ask for something that hasn't yet reached Asia Pac, and we use some fallover logic in the CDN to go, if you can't find it there, try all of the other servers first. Doing that made the registry publishes twice as fast, which was a pretty cool thing to have done 2 weeks ago. Nearly out of time. Next is the website, and this is where SOA really begins to pay off because there's almost nothing new here. Everything else here you've seen before. The only new things are the registry API and Elasticsearch. These are two new followers. The registry API is following everything in the database, and it's turning it into a relational registry because Couch is not a very good database. It's really only good at being an event queue, so you can't really query it very efficiently. But relational databases, they're really good at being queried, so we copy everything into a relational database, and that is what serves the website. The other one is Elasticsearch. Elasticsearch is another database optimized for search, and there's a follower that fills it up with stuff without having to do a direct copy all the time. I'm going to go a little bit faster now. Finally, there's NPM onsite, and this is where I get really happy about SOA because NPM onsite is literally a copy of the registry architecture. It's exactly the same services, exactly the same code, just crammed down into a couple of Docker containers and deployed wherever it is that you want it to be. Which is great, because it means that when our customers find problems in NPM onsite, we fix them there, and suddenly the whole registry works better, and vice versa. When we fix something in the global registry, NPM onsite works really well. And it also means that we can be super confident about the scaling abilities of NPM onsite, because until your corporation is as big as all of the other JavaScript developers in the world, NPM onsite is going to be able to handle your load. There's a couple other cool things going on that I'm probably going to skip through, because I'm pretty much out of time, I think. So some takeaway messages. SOA is pretty neat. Node is pretty good at SOA. U2 can be really good at SOA. And NPM is pretty neat. Thank you very much.